material. But why is it that steel is one of the most favorable construction materials? And the third one is, why should you be attentive during lectures? I think this question has already been answered by Shravan, that if you just zone out for some time, then it's gone. But more importantly, and I already said that it is relatively more challenging in this setup, wherein there are hundreds of ways to keep you distracted. But so what I'm deliberately going to try to uh, uh, solve this problem or resolve this issue in this particular semester is I'm going to shift my focus for internal grading from tests or from assignments to the involvement in the class. Okay, so there is going to be less emphasis on your marks in the test, and there's going to be more emphasis on how attentive you are during the class. Now, it's difficult again because the videos are off, and and I'm really not here to police you कि भाई कौन सोया है कौन देख रहा है कौन. I don't believe in this bullshit. If you want to pay attention, you're going to pay attention irrespective of what the setup is. But now, there has to be some kind of control over, if I'm reaching you, if you are able to understand, what I'm saying. So there's going to be there are going to be frequent discussions after every topic. Okay. And you have to make sure that if I call your name, you have to answer me. And failing to do so for any reason, I'll perhaps observe for some time. If you fail to respond to that, it's this is a policy that I'm strictly going to follow this semester. That I'd ask you to leave the meeting right there, then and there. And I think now this might sound a little unfair initially, but if you think it's a collaborative effort, and we just meet for 100 minutes per week. And if you historically the load for theory of structures has been very less. So I think if I am giving you my time and attention, I really want you to reciprocate the same. And believe me, at the end of this course, we will definitely turn this Sotela bhai into our Saga bhai. So that's my guarantee. All you have to do is get into the bus, and the rest is up to me. So I'm not going to promise you that the lectures are going to be damn interesting. The lectures are going to be as interesting as the Family Man or so on. It's normal, but we are going to make it as playful, as easy, and as understandable as possible. So there's not going to be a lot of jargons. The outriggers, this and that system, this system. Very simple, very simple. But whenever you don't understand, it's your job to ask me a question. If you don't ask, then I'll have to ask, and if you don't answer, then I'm going to ask you to you know I'm not saying I want right answers. I'm just looking for discussion, so that we uh, are we again make sure that we are moving in the right direction, and whatever I'm intending to teach reaches you. So just to give a small disclaimer. So to just kick off with a light start, this is there's just a series of questions that I would like you to answer. Okay. Now this is voluntarily. I'm not going to point out people to answer this. This is just voluntarily. If if you really know about the structure, if you really know about this building, then just you're free to speak. So can someone answer as to who were the architects of WTC New York? Come on, architects.
We know the engineer was Leslie Robertson because we did a study on him last year. I mean, last semester. I think the architect was Yamasaki.
Yeah.
Yeah, all right. I think there were two. I remember Minoru Yamasaki. Okay, all right.
Yeah. So these are the architects of the World Trade Center, and as she rightly said, the structural engineer was Leslie Robertson. Leslie Robertson. Now, I happen to work at Leslie Robertson Associates, Mumbai. So I'm glad that you know it. You know the person who designed designed these towers. So just to give you a little more background, that these structures, I mean these towers were built in a span of 5 years. Only 5 years. It's a 110-story building in only 5 years. Can someone answer as to how is it possible to do it in 5 years? Like our projects, 15, 20 stories take forever to complete. So 110 in 5 years. What was the prime reason for that?
Wasn't it mainly because it was a modular system? I'm sorry. Like the
Uh,
design, it had a particular way of design, right? Because it's a repeated structure after a point.
Yeah.
So that definitely made things smoother. But I think that's only a part of the reflex. There should be something bigger which I'm missing out.
Okay.
But
Your
I
answer is
know
partially correct. It's modular. Yes, it's modular. It's it's repetitive, and therefore the planning and the design is simple. But in terms of construction, what could be the main factor that you're able to achieve such a speed?
the
Maybe
material.
it was prefabricated.
Exactly, because it was prefabricated and it was steel. So it was, just bring in all those members and just, connect them. So it was just bringing them, sort of connecting them. It is a prefabricated. All the, so and does someone know what type of structural system is employed here? Okay, it's a tube system. I'm not going to get into what it is,
Two
but
cores, right?
sorry.
Two cores, right? One holding the internal parts together and one holding the external parts together.
In a raw sense, yes. So
Yeah.
there's an external tube and there's an internal tube. So that's called
The
tubing here.
hollow internal, the hollow core was the internal core was hollow and the external core had. Oh no, the internal core had the full structure and the external core was made free space for the.
Okay, so he's partly correct. It's tube type structure wherein you have a very closely spaced column towards along the perimeter, which are connected by very stiff beams. So they form a tube, and they form the major lateral resistance system. Moving to our next question. So which factory is on the path of becoming the largest building by footprint in the world? Who Elon Musk fan?
The Tesla mega factory?
Yes, it's the Tesla Gigafactory. So just to give you a sense of how big it is in terms of its footprint, you can see the comparison with different towers. And the thing about this factory is that it is going to be entirely powered by renewable sources of energy. Then it is estimated that this factory will be built at a cost of 5 billion. Now I just want you to remember this number for a while because we'll get to some other example and then we'll see the cost comparison. And it is also estimated that 100 such factories could power the entire world. So you just understand the scale of it. Next one. In which year were the Olympics Games first played at the stadium?
Sorry, but your voice is a bit muffled, I think. I don't know if anyone else or not, but it's a bit
Yeah.
muffled.
Okay, just give me a moment. Is it better now?
Yes.
Okay. So the question is, in which year were the Olympic Games first played at the stadium?
This is 2008 because it was the nest egg, highly criticized Herzog and de Meuron building.
Yes, so this is the Beijing National Stadium, which hosted Olympics in 2008. A very complex structure, perhaps one of the biggest steel structure in terms of the use of material, and it is the most complex stadium in the world in terms of its structural system. So the intention of all these covering beams was to sort of uh, cover the columns that support the retractable roof. I hope you understand what the retractable roof is. But over the uh, planning of over the planning periods, the retractable roof was removed. So there was no need for providing these columns which support the retractable roof. But nonetheless, this system was they seemed so aesthetic that they decided to continue with the network of beams that they were providing, even though they had no structural function altogether. So a very complex structure, but it's good looking, right? You see it and you marvel at it. Then this one, in which city is the CCTV tower located?
China.
Yeah, but in which city?
Beijing.
Yeah, Beijing. So over the world, there's this race of going tall. Now, we start with 50, 60, 100. Now we've gone to 180, and there's still companies that are trying to go tall. So it's if you look at it in one way, it is just we are going high in two dimensions. We're just increasing the height. That's it. But then China came in and they said that we are really not in the race of going tall, but we can really make our structures truly 3D. So this structure really gives a 3D experience. And the cantilevers, the maximum cantilever is of the order of 75 meters. So you can imagine the kind of complexity the structural system would have had to span 75 meters of cantilever. So perhaps if if required, we could always look at structural systems like this, very different, but have worked great. Everybody knows this. So who are the structural engineers of Eiffel Tower? So इतने time में you can Google an answer.
I know the architect. I don't know if that was an engineer.
Okay, just tell me the architect.
Eiffel, the guy.
Who's yeah.
But
Uh, I did not hear you properly. Did you answer
I
who's
don't
the
know if he
architect?
was the engineer. I don't know if this sort of structure required an architect or an engineer, or required an architect in the beginning.
Yeah, but who was it?
Gustav.
I only know Gustav Eiffel.
Okay. It's a very common misconception that Gustav Eiffel was the designer of this, and therefore it is called the Eiffel Tower. But actually, Gustav Eiffel was the guy who built this. It was his company who built it, and of course, he took the initiative of building it. But the responsibility of designing this tower, was on the shoulders of Maurice Koechlin and Emile Noguer. I'll just leave that pronunciation to you. So Maurice Koechlin, I think you already know this name. He's the great grandfather of Kalki Koechlin, and Emil is not a structural engineer per se, but he's a civil engineer and an architect. So now you can imagine if an architect can design a steel structure as good as Eiffel Tower, yeah, you also can do it. You can also, the objective is blur the lines between what an engineer is and what an architect is. Okay, so our objective is not to think from an architect's perspective or not to think from a structure. Just you just have an holistic approach as to what can work as a system. So previously we did not have this distinction as a structural engineer as an architect. So even an architect can design such a complex structural system. So definitely something that we've loved over years and it's going to be loved forever. This one. So is your favorite football team from the city of these towers?
Is this in Barcelona or Madrid?
What is it?
I don't follow football, but I'm assuming these are either these seem. I think I've seen these before somewhere.
Yeah.
Madrid.
In somewhere in Spain, are they?
Did someone just? I think that was what I was looking for.
Madrid.
Madrid. Okay. So the first thing is that you don't have to be a fan of football to answer this question because the question is your favorite football team from the city of these towers? The answer could be yes or no. It has nothing to do with these towers. Jokes apart, it's person who answered Madrid is correct. These are the leaning towers of Madrid. The name is Porto de Europa, which means the gates to Europe, and this is located in the financial district in Madrid. Now, can someone guess what is the inclination of these towers with respect to the vertical? Meaning as to what is the angle between this vertical element that you see and this inclined element?
15 or
30 degrees.
20.
Wow, that's perfect. Like, the first time I got a perfect answer. Now, people start with 3, people go to 60, and then somewhere we average out to 15. But yes, 15 is the correct answer. Now, 15 might look like a small number, but in terms of designing a system for it, it's very complex. So it has a core that goes from top to bottom, and then there are these tendons which sort of hold this structure from falling in this direction and this structure falling in this direction. So it's a very complex structural system. Next question. This structure is likely to be on the campus of which type of organization?
Laboratory.
Sorry. Could you be a little louder? Like,
A university.
yeah, university. Why would you think this should be a part of university?
Or a
Something
museum.
देखो भाई,
maybe like an exhibition space.
देखो भाई थोड़ा imagine करो. This resembles something.
It looks like an airplane wing.
Exactly. So
fin of an
it looks like, you know, the backside of the plane, and this is actually a part of the U.S. Air Force Academy. This building is called the Center for Character
Wow.
and Leadership Development, a monumental name for a monumental structure. And in structures like this, the lines between architecture and structural engineering really blur. There's no, I'll plan this and you design this. You have to work in close collaboration to come up with something like this. So, the first example that we saw was, Eiffel Tower, and then an example like this. So the way it is planned is it sort of points towards the North Star. If you're a fan of World War movies, you would see American planes, and they always have this star on their plane. So the North Star is sort of the guiding principle of their academy, and therefore it has been aligned with the North Star. So what is important for us? It's really a fusion of architecture and structural engineering. That's what important for us. And then this one, I'm sure that you must have seen this. So a simple question is, which living being does this structure resemble?
A dove.
Yeah, I mean it was meant to resemble a dove, but it could resemble a number of things. It could just resemble a Pokemon. It could just resemble a dinosaur carcass. It depends upon how you want to look at it. But Calatrava wanted to sort of make it look like a dove. So the cost of this project is 4 billion. Now I just want you to go back to Gigafactory, and the cost of a Gigafactory was 5 billion. 100 such factories could power the entire world. This entire this single station came at a cost of 4 billion. So you can imagine it in terms of how expensive this project is. And if you get into today's market, you will realize that it's all about money. It's all about how cheap or how cost effective you can keep things. Yes, beauty is important, aesthetics are important, but our economy, our market is driven by cost effectiveness. If you can save your clients money, you're going to be on board, and you're going to be doing projects. It's all about being cost effective, and it's all about being in time. It's all about saving time and saving cost. So a very expensive and a very uh, a very controversial project, I would say. This is a very simple one. Almost all of you might have been here. So which is the third largest airport in India? Sorry.
Is it Kempegowda?
Yes, it's Bangalore. It's Kempegowda International Airport, Bangalore. Now, it's an amazing airport. You go in, you really feel good. The lounges are extremely good. But the thing about this airport is it has got a gold LED rating. It's so it is highly efficient in terms of its energy use, sustainability, and so on. So another example. We are moving towards the end, and we'll understand why we are looking at this example. Yeah, please go on.
It's a suspension bridge, right? Golden
Yeah,
Gate gets destroyed in almost every
it's a
movie.
suspension bridge. So what I'm realizing it is that year on year people are getting smarter, and I did not used to get answers so quickly, and I really had to wait for a long time. But here, you guys are already before even I finish my question, you have your answers. Perhaps I should perhaps now move towards more difficult questions. Nonetheless, yes, it is suspension bridge, the Golden Gate Bridge in San Francisco. Uh, the speciality of this bridge is it was built about 4 years and 4 months, and it was built ahead of schedule. and in lesser budget. So this is something that we're really not used to here. Whenever we start with a project, it overshoots almost every time in terms of cost and money. Uh, you know, uh, an example of it is the Bandravali ceiling, which took a lot of time, took a whole lot of money to finish. But this is being built in a period when we really did not work that mechanized. We did not have those, giant cranes and giant equipment. But nonetheless, it was finished in just 4 years and 4 months, and ahead of schedule. And then let us look at something domestic. In which of India's megacities is this bridge located? It's a difficult question. It's very rare that I get an answer to this question, and I always wonder why.
Is it somewhere in Gujarat?
Gujarat. Okay.
Bhopal,
Any more? Sorry.
Bhopal.
Bhopal. Okay. Okay. That's an interesting answer. First time. So this is basically the signature bridge in New Delhi. So in the outskirts. I know it's a little difficult to connect anything that is good with Delhi. No options there. But yes, this is the first and only asymmetric cable bridge in India, and this is a cable stayed bridge. I just hope that you understand the difference between a suspension bridge and a cable stayed bridge. If you don't, just Google something. Just Google it after the lecture. So what are you likely to see inside this building?
A play, and on the outside of
Sorry.
it, you're likely to a play. Orchestra, sorry. It's an orchestra hall.
Okay. And on the outside.
On the outside, probably like, your shoes getting stuck to the pavement before it was matted out.
Exactly. So this is you can expect performing arts. This is Walt Disney Concert Hall, and it has been featured in a number of famous movies: Iron Man, Any Iron Man Fancier, then Alvin and Chipmunks, and perhaps the first premiere of Matrix Revolutions was in this uh, concert hall. So the reason why he said is that you might, if you're standing outside, you might, you find your shoes stuck in the pavement, is because this is a series of concave and convex shapes. And concave shapes are very tricky because they have this tendency of, taking in sunlight from a very large area and concentrating it to some points. So after it was built, people were very happy. The real estate price went up in and around, but later on, people realized that their electricity bills were shooting up. No, and for a few houses, of course, not for all the houses. And they were wondering what the hell is happening. Why are the electricity bills shooting up? And after a lot of observations and after common experiences, it was realized that some parts of the structure had very polished, mirror-like finished panels, because of which the sunlight was getting concentrated at a few locations, and the temperatures were shooting up to 60 degrees centigrade, and therefore their air conditioning costs was going up, and therefore their bills were going up. Then after all these complaints, they ultimately came and finished the surface, and then the problem was resolved. So you never know if you're trying to plan something as beautiful as this. You just never know what could come up. So what is the common thread in all these different types of examples that we've looked at?
Steel.
Steel.
Exactly. These structures are either partially or completely made from steel. So now, we sort of understand what is the potential of steel as a construction materials in terms of its versatility. We can build almost anything with steel. And this is not only because of these examples, okay? In very common Ghar Ka commercial projects and residential buildings as well, whenever there's a complexity, whenever there's a complex shape, geometry, size, transfers, anything, the first material that we think of is steel. But flexible, it gives a lot of flexibility to architects as well as structural designers. And it might not be the case with concrete. The concrete as a material has its own limitations, and then it's not as strong as steel. It does not have the strength and weight ratio of steel as steel has. There's always a question of complex geometries and complex structural elements. So why you as an architect should understand what steel is, because it is used at so many places. Okay, and if you are a very imaginative architect, that you really want to build something that is iconic, more or less definitely you're going to there's a high chance that you're going to use steel in your planning, in your design. So, with this thought that somewhere down the line we are going to use this material, that's for sure. Yeah. Now, if you're doing normal projects, uh, if it's not really a signature project, there's a very high possibility that we'll use concrete. So, but this is just a personal opinion. But for more than 80 to 90% projects that you will do, you'll use concrete. But for very complex projects, or very or industrial projects, or projects that are very special, there's almost 100% probable that you'll use steel. So that sort of gives us the background as to why should we study steel. But what are we really going to gain out of this course to reach there? So is it that after doing this course, you'll be able to design something like the Walt Disney concert, or you'll be able to design something like the Eiffel Tower? What do you think?
Hopefully, I mean, hopefully not Walt Disney Concert Hall, but yes, uh, something really innovative with structure.
Okay. Any more opinions on this?
We can not only design it but also make it in a real sense. Like there are many things which still can help us to do.
Okay. Any more opinions on this? Okay, so to break all the myths, after this course, you'll definitely not be in a position to, design something like this. But you will be strong with your fundamentals. You'll sort of get a hang of what works and what doesn't, and what is the practicality of a certain size, of a certain span that you're expecting, and that sort of gives you a background to start to think in that direction. So, as I said before, here we are not looking at steel from a system point of view, but we are going to look at it more from an element point of view. How do these elements work independently, and how do they work when they come together? And once you sort of get a solid foundation on this, then it's all up to you to build on that foundation. Perhaps in your next semesters, you might encounter courses which work on structural systems, and then you'll understand this better. But right now, we are going to work on giving you a solid foundation on steel design. Now, it's not that this, since we're not studying structural system, then there's nothing really to learn here. A basic question that I get in every ADS project that you guys do: which size will work and which size won't? Now, this is a very simple question, and uh, you just now, so it's not that I'm able to answer these questions every time, but then for something similar that I've done, I've got a sense of what works and what doesn't. And after we look at numericals, after we look at numbers, after we look at span, and then after we look at what works and what doesn't, even you get that understanding. And this process helps you understand how to arrive at a particular size. So when you simply ask, no, will this work or not? It's not really a simple yes or no question. It has a lot of background to it. There are a lot of complex calculations involved to arrive at an answer of yes or no. Now we're not going to get into those complex calculations, but definitely we're going to look at the easiest ones. Okay, this is the minimum. Boss, if you want to look at a beam size, this is the minimum calculation that you'll have to do. And speaking about practicality, uh, I don't think you guys really get into, when you actually start practicing, you don't really get into calculating all this, and you just hire a structural engineer, some poor structural engineer like me. You just hire and then say, buy sizes, they will pay you whatever, and then the sizes are ready. But the add-on that you will have as an architect, key, you will understand if whatever the structural engineer is proposing, is it really required or not? If he is, if he is giving you certain sizes, you should have an understanding of, how is it optimal? Is it oversized? Is it undersized? Because ultimately you are going to be the boss of the project. So a boss always have to understand at least the ABC, if not ABC up to Z. Okay, so that is the reason we are going to learn the ABC of steel. We're not going to learn ABC up to Z. That's my job. That's not your. So that is something that you should expect out of this course. So now to actually start, I'll just start the recording. Oh, the recording has already started. So it's structural steel design of primary elements. As I said before, we are going to work at element level. Then I think it's enough to finish this course in 16 sessions of 100-minute each. But I think this semester we have 14. We have 14 weeks, so we are going to just squeeze in 2 sessions here and there. There's going to be one theory paper of 2 marks and of 2 hours, and the maximum marks is 50. Minimum passing marks is 20, and the internal marks is 50. And as I said before, the internal marks, the focus is going to be on your class participation, and less focus is on the various exams and the various assignments and so on. So it's really important that you pay attention, you answer me, you answer my call, even if you don't know the correct answer. You answer my call. So just so that you know who I am. I am a senior engineer at Lera Consulting Engineers. I've done my master's in structural engineering from IIT Madras and KIT in Germany. I passed out 5-6 years back, 5-6 years back, and since then I've been working as a designer for mid and high-rise structures at Lera. So just getting an overview of the syllabus. Give me a moment. Okay. So we are going to begin with. So though it is not mentioned in the syllabus, but I think that it's very important for you to understand. We are going to begin with material. What does steel have that it is so famous, and it offers us so many. What are the advantages that steel offers as a material, and uh, why that so many designers really tend to choose steel. So we looked at it from an example point of view. We looked at n number of examples and then say कि अगर use हो रहा है तो there has to be some sense. But मतलब as a structural material, what does steel have that it is just so versatile? That's number one. Then we are going to look at what is called as the steel table. Now every product comes with a catalog. Okay. For example, if you just go to an LG showroom, you'll have a catalog of everything. You'll have a catalog of fridges, you'll have a catalog of this. Similarly, all the manufacturers of structural steel elements have their own catalogs, and these catalogs are called as steel tables. And this table sort of gives you a lot of information about about various types of sections. So we are going to understand how to read that steel table. कि ठीक है, I have ISMB. Let us say I have a section called as ISMB 500. So what does that ISMB 500 mean? What are the properties of ISMB 500 that are important to me? How to read the steel table, and how to interpret this steel table. This is something that we're going to look at. And then we are also going to look at what are the readily available steel sections in the market, because there are uh, hajars of sections, but not all of them are really available. There are only select few which are very commonly used. So that is number one. Number two is you're going to understand connections. Now, this is these all these different elements they're going to be connected. They are all prefabricated. They're going to be connected. So we are going to look at different ways of connecting them. We're going to look at rivets, bolts, welds. We are going to look at the advantages, disadvantages, and suitability of them. And if time permits, we are going to do a simple design. Ki boss, if we have this amount of tension force, how much bolts do I need? We are going to do this very simple calculation. And this helps us in sort of getting you an understanding of detailing the connection, which is I think a very important part of any structural steel project that you do. And lastly, we are going to actually spend a lot of time on this, on members. So we are going to look at different types of members. For example, if a member carries a lot of tension, it is called as a tension member. Then we look at what our tension members are, how they are designed, and so on. Similarly, compression members, we are going to focus on beams. And finally, we are going to look at foundations. So we are not going to design foundations, as in we are not going to learn how to size foundations, but obviously we are going to see different types of foundations and their suitability, and how to use when to use which type of foundation. So this is a syllabus overview, very simple, very straightforward, and nothing complex there. So uh, we are going to spend a lot of time on members, because this is where all the calculations are, and we are a little bit scared of calculations of numericals. So we have to make sure that we spend enough time there. The books that I personally would recommend to refer is The Design of Steel Structures by N. Subramanian. So this book, for this course, this is a go-to book. Anything that is being taught in this course, you will find its reference to this book. May it be theory, may it be numericals. And if you are super excited about this course, and if you really want to get to the roots of it, then there's the book on the right side, which is Steel Structures by Salman Johnson and Malas, a very famous reference book in the US and India as well when we actually want to learn some concepts. So it's great if we could get a copy of either one of these books. So the course objectives, as I said before, we are really not going to get into some complex jargon. Try to keep it simple. We're going to try to develop a solid background on the principles of structural engineering design. Okay, we're not going to design a structure, but principles samajh mein aa gaya, so you can build on that later in your further courses. Then we're going to spend time understanding theories and behavior of steel design, behavior of various elements in steel. And then we are going to spend some time in hands-on design experience through assignments. Now, when it was a class work, or it was a subject based on lectures, physical lectures, it was very easy to do these assignments, and then but now it's a little challenging. But nonetheless, I sort of design the tests in such a way that you solve a numerical while solving the test. Not directly, you're not expected to solve a big two-page numerical and then submit it, but the questions are framed in such a way that step by step you have to design it. So assignments are done that way in this course. And finally, this is something that I can really add to, and this is something that I can really bring value to this course is because I've been practicing, and there are very different types of structures that I've handled as of now. So there are very common challenges that we face as structural engineers, and that those are the challenges that I could really share with you. And I could perhaps add into how architects can work during their planning so that these problems do not come in the construction stage or in the design stage and so on. So perhaps we could have discussions on various projects and how they've worked and how they're not. Now, whenever we have a problem in life, whatever it is, like breakup हो गया और पास नहीं हो रहा है और क्लास में ध्यान नहीं लग रहा है, whatever, we sort of go to God and pray कि भाई कुछ solution दिखाओ, right? So now even this course has a God, and that the name of that God is IS 800 2007. This is General Construction Steel Code of Practice. Any questions we have कि भाई कैसे डिजाइन करना है बताओ, टेंशन मेंबर कैसे डिजाइन करना है, कॉलम कैसे डिजाइन करना है, just go to this code. It lays guidelines for designing construction. It will tell you कि boss, if you are designing a beam, this is the ways in which it can fail. So you just follow what we are saying, and at least the structure is going to stand perfectly. कोई problem नहीं होगा. So this basically lays out guidelines, and it ensures adequate structural safety. And every clause in this document is based on a lot of research. Uh, so it might be an actual research, or it might be based on observations over decades. So everything has a very solid background. So if it says that this type of failure might occur, there's a very high possibility that it will actually occur. So this sort of renders the task of a designer simple. Now, when I get a project, when you give me a project, I cannot sit and start researching about how steel behaves and what failures to look at. So since I have a document, I know how it can fail, how I can mitigate that failure, and therefore it makes my job easier. And then there has to be a consistency among different designers. Now we agree to this that planning and designing is a very creative task, right? But that does not mean that if I am saying that ISMB 500 will work, tomorrow some other designer would come and say that no, this is too much. ISMB 100 will also work, or 150 also. There has to be a consistency, between how different designers function, and the code makes sure that there is a consistency there. And finally, it has a legal validity. Tomorrow, if something goes wrong with the structure, the first investigation that will happen is, ki, bhai, did you make it according to the code or not? If you made it according to the code, then perhaps it is not a design fault but a construction fault. But if it is not according to the code, then it can be very dangerous for the design. So steel has this code called IS 800, and even concrete has a code which is IS 456. These are just a few of many documents that uh, perform all these functions. So I think we'll take a short break, 5 minutes, just freshen up, because now we are going to actually get into the course. This was just a upper introduction, but now we are actually going to get into the course. So I just want you to take some time, freshen up, come back, and listen intently. So it's 11:37. Let's meet back at 11:42. In the meantime, if there are any questions, I'm available.
I have a kind of out of syllabus question related to a personal project.
Yeah.
So I'm actually helping an acquaintance of mine with his gym on his terrace. Nothing major, just like steel roof cantilevering of the this thing. He just wanted me to draft the plan for it, his terrace ka plan,
Yeah.
after sending me sketches of it. So he was asking me if it's possible to, like, during the rains water will come in if it's just a roof covering cantilevered of the wall.
Yeah.
So he was asking if there's any way to like hang like a polythene sheet or something that permanently kind of acts as a curtain. So so to add that onto the just the roof, would that weigh down too much? Because he's thinking of like a steel roof only by the looks of it. How the contractor or whoever they get to do it is definitely this thing. It's a building project, so he has to first submit a proposal and everything.
Okay. Okay. Okay.
So
I think we can discuss this once we're done with the lecture, because it will
sure.
take me some time to really understand all the details about it, and then we can discuss.
Thank you so
Let's
much. If you
let's
will
wait
help
it
me,
up till the end
great.
of the lecture. Yeah. So apparently, I forgot to unmute my mic, and I've been talking for the last 2 minutes. Am I audible?
Yes, yes.
Yes, yes, you're right.
Yeah. So, so any material has, its own property that sort of outperforms all the other materials. For example, concrete has a very high compressive strength. Then, even we as individuals have certain property that, in that we are relatively better than others are. If you're talking about steel, this property is its tensile strength. Steel is all about tension. So, when we say that it is strong in tension, what do we really mean? Let us just put some numbers there so we understand. In order to put some numbers, we have to do this test called as standard tensile test on a machine that is normally called as universal testing machine. And this test is performed on, it can be performed on various, on various samples of steel, which are called as coupons. So, the various shapes are shown on the screen. So first, let us look at, how the test is performed, and then we look at the significance of it. Okay. So what did we principally do? Now, so this was just perhaps an ad video of some company that produces these machines. What is important for us is that there are various ways in which this test is conducted. The objective is same, and it can be met by using different types of specimens and different types of measuring equipment. So, what have we done in this test? Anybody? I don't want a very technically correct answers. See, what did you observe and what did we do?
They were trying to see how well it performs when certain forces are applied, right?
Yes, but but what did we particularly do in that test? Yes, we're looking for how it performs, but क्या किया हमने मतलब?
Stretched it till its breaking point,
And
increasing the friction.
exactly, so we just fitted the specimen in these in that machine and we stretched it. So we applied actual tensile force in it, and then we had measured how much is its length before, and then we sort of stretched it until failure. While sort of looking at what is the increase in the length at various values of force, and then we noted what is the the force at which it breaks. And now if you can see the specimen before and after the test, you can see how much it elongates. So it gives you a feel of how ductile steel is, or how much tension can steel take. So let us again look at a video as to what actually happens. Now the machines that we looked at were highly digitized, and they gave very so let us try to understand as to how to interpret this particular test. Give me a moment.
Okay, so the test has just started and we can see that the sample is being stretched outwards. That little kink that you've just seen in the graph is known as the yield point. That indicates the transition between the straight line portion and the curved part of the graph, and indicates the transition between elastic deformation and plastic deformation. We're about to reach the peak of the graph. The peak is known as the U point and indicates the ultimate tensile strength of the material. Beyond the U point, the material is weakened and the force is falling off. Beyond the U point, the material is on its way to failure and nothing can stop it from failing now. Can you see how the sample is beginning to reduce in diameter? This is known as necking, and the sample is about to fail.
Okay, just a moment. I think the video lagged a little. That's why I just played
Okay, so the test has just started and we can see that the sample is being stretched outwards. That little kink that you've just seen in the graph is known as the yield point. That indicates the transition between the straight line portion and the curved part of the graph, and indicates the transition between elastic deformation and plastic deformation. We're about to reach the peak of the graph. The peak is known as the U point and indicates the ultimate tensile strength of the material. Beyond the U point, the material is weakened and the force is falling off. Beyond the U point, the material is on its way to failure and nothing can stop it from failing now. Can you see how the sample is beginning to reduce in diameter? This is known as necking, and the sample is about to fail. We've just seen a sudden dramatic failure and we're left with a jagged fracture.
Okay, so to understand this graph, or to understand this behavior, what we've done is we've used a graph. Now, what do? You plot a graph with say days on the x-axis and number of patients on the y-axis, and then you get some kind of curve which gives you a feeling as to if you are getting into a wave or getting out of wave. This is a flattening. So these plots help us to understand some behavior. The graph that we are going to use here is what is called as a stress versus strain curve. Okay. So the question is, what is stress? I feel it is very basic, and you can definitely answer this. What is stress? Right? We all take this every day, day and night.
Sorry, my mic was. Stress is the force that's being applied, and strain is how it deforms under that force.
So what is the difference between stress and force?
The stress is the force applied as a pressure, like the volume of the object or the area of the object, within correspondence to the force applied, and the strain is the original length of the object versus how much it was actually, how much that original length was changed. So there is one which is a force applied, and one is the result of it.
Okay. Any other additions to this?
Oh, you're very soft actually. Like we can't hear.
Any other additions to this?
Thank you.
Simple question, guys. What is stress? We take this day and night.
Your voice is coming out a bit soft, and I think some students are experiencing audio issues.
Okay, is it okay now?
Yeah.
Perfect. So the question is, what is stress? Okay, we take this day and night before exams, before submissions, before a number of events. So what is stress? So Shravan said that stress is force applied as a pressure. So are there any other opinions about it? Any other thoughts about it? Bolo bhai, it's a very easy question. Wake up and answer.
It's just reaction of the force applied by the material.
Reaction of the force applied. Okay, so he has given a 50% correct answer. Nobody?
It is specific to per unit area.
So you mean to say it is force upon area?
Yeah.
Okay. So Bhavik is 50% correct here. Okay, so let us try to understand it this way. Mathematically speaking, stress is force upon area. It is completely correct. But let us take this example. Say I have told you that I'm going to conduct a very difficult test. Next Saturday, and Pranjal is really determined to do well in this test. But somebody else, say Anup Kumar, is say like, "Kya test hai na? Matlab, what?" So Pranjal is going to be under a lot of stress and she's going to study. But Anup Kumar perhaps is okay with not scoring that great in the test. So the thing is, I have applied the same amount of force, but the reactions are different. The reaction that I'm getting from Pranjal is developing a lot of stress in her, and the reaction that I'm getting from Anup Kumar is perhaps not developing stress at all. So then when we say stress is equal to force upon area, how is it that even though the force is same, the stresses are different? So a slight correction in this definition is stress is actually the resistance force per unit area. Now, then why do we say it as force upon unit area? Because a great person said a long time back that every action has equal and opposite reaction. So the reactive force is equal to the applied force. Therefore, we said that stress is equal to force upon area, but it's actually the resistive force upon unit area. So that is what stress is. So here, but pertaining to this particular case, the stress that we are going to take into consideration is the force applied upon the cross-sectional area of the coupon. I hope you understand what is cross-sectional area. Going back to the presentation. So this cross-sectional area of the coupon. So that is what area is. So when we divide the force upon area, then we get the stress that is getting developed there. Okay. And next question: what is strain? Okay, we have different strain.
It's change in the material after applying force on it.
Change of the material. So what is
Like,
changing about the material?
length, area, volume. Any in those terms.
Okay.
Deformation.
Deformation.
Like it'll stretch and pull out and then bend. If it's steel, if it's in tension, if it's in compression, then compressive load will just crush it.
Okay. So, let us try to use some specific terms here. So, it's an axial tension, okay, meaning that the tension is being applied in one direction. What is happening because of that is that the length of the specimen is increasing. Now, we want to measure or we want to put some numbers here. So, we use the phenomenon, the term called as strain. So, strain is the ratio of change in dimension to original dimension. So that sort of gives us a feeling of, or that sort of gives us a sense of how much is the change in dimension, referring to the original dimension. So I hope these definitions are clear. Stress is the resistive force upon unit area. Since every force is every action has an equal opposite reaction, we called it force upon area. And strain is change in dimension upon original dimension, and therefore you can see that the unit here is mm per mm. So mm is the change in length, and then another mm is that the original length. And the unit of stress is MPa, which is also Newton per mm square. Note these things down if if you don't know them already, or if you tend to forget. So this is how mild steel behaves. Now there are different grades of steel. There are different grades of concrete, M20, M30, M40. Similarly, there are different grades of steel also. There's mild steel and there's high strength steel. Okay, we are going to look at only the common types. We're not going to look at all the types. So mild steel, it has the yield strength. Okay, we'll look at these terms, but just to start with, mild steel is a steel that has a yield strength of approximately 250 megapascals. So this Fy value for mild steel is approximately 250 megapascals. Okay, now we'll get into what is yield strength and on later. But just look at this graph right now, and I want you to draw this because we are going to look at a number of terms later on referring to this graph. So I just want you to have this in front of you. So when we start loading the specimen, what we observe is initially the stress is directly proportional to strain up to a certain point. Let's call that point A, and this point is called as proportionality limit. Simple. Stress is proportional to strain. Therefore, we call this, the limit as proportionality limit. So up to this limit, stress is directly proportional to strain since it's a straight line. And when this happens, we say that the Hooke's law is followed. So Hooke's law states that Hooke was a scientist who worked on this, and Hooke's law states that stress is directly proportional to strain up to yield point. Okay, then the slope of this line, the slope of this particular line, which is the y, the y term upon the x term, the y coordinate upon the x coordinate, is called as Young's modulus of elasticity. Okay, so the law which states that stress is directly proportional to strain is called as Hooke's law. Hooke's law is satisfied up to point A, which is called as proportionality limit. And the slope of this line is called as Young's modulus of elasticity. Okay, so so what is the significance of this straight line? कि मतलब क्या है straight line है तो क्या मतलब है? What this means is that the material is still elastic. Now, what does it mean? कि material elastic है मतलब क्या है? So what it means is, if you apply load, it will deform. But if you remove the load, it will go back to its original length. Rubber le lo. You say rubber is elastic. Why do you call it elastic? Because you stretch it, it deforms. You release it, it goes back to its original position. That's why that is why you call it elastic, right? So O2A is a linear elastic zone in which if you stretch the material, if you apply tensile load, it will deform. You remove that load, it will go back to its original position. And that is why this zone is called as elastic zone. Okay, this is a linear elastic zone. After point A, the material does not behave linearly. So it is still elastic up to point B, but it is not linear. The variation is not linear. The stress increases, it does not increase linearly with strain. So the zone from the origin up to point B is called as the elastic zone. Out of that, OA is the linear elastic zone and AB is the non-linear elastic zone. Okay. Don't worry that I'm using a number of terms and you're forget it later. Everything is there in this presentation later. But I just want to, since we're looking at the graph together, I just want to explain these points and perhaps we can look at it again in the subsequent slides. So OA is a linear elastic zone. मतलब क्या? कि अगर you remove the load, it will go back to its original length. So it's elastic. And AB is the non-linear elastic zone. Now, if we stretch it further, if we increase the force further, what will happen is it is going to yield. So it reaches a certain point C, which is called as the upper yield point. Okay, yielding is basically there's a you see this plateau here. So yielding is when the plastic deformation starts occurring in that material, meaning that if you are beyond point D and then you release the load, then it might not get its original length back. Okay, it will, of course, it will shrink. It will, try to go back to its original position, but because you have stretched it so much that it will not get back to its original position. Taking a moment here, are you understanding what I'm trying to say?
Yes, yes.
Simple, right? It's just that you don't overdo something. If you overdo it, perhaps you're not going to get back to what things were before. So similarly, if you stretch it or if you load it beyond point D, it might not gain its original length, and that is when we say that it has undergone plastic deformation. Plastic, pata hai, you deform plastic, it does not go back to its original position, and therefore this is called as plastic deformation. Okay, so point D, we saw that video in which the graph was something like up and down here, but more or less same value, or mean value was same. So this D point is very significant, and that is what is called as yield stress. Matlab this, after this stress, perhaps it will go a lot of deformation without, providing any resistive stress. So between D and E, it undergoes a lot of deformation without any increase in the stress. So D is called as the yield plateau. Then we reach the point E, but suddenly what is observed is there is some reconfiguration at the atomic level, and suddenly the capacity of the material or of the member to take load increases. Therefore, as we load it beyond point E, what happens is there's again an increase in the stress. So the increase in stress, meaning what increase in stress means is that the material is now resisting. It is saying ki bhai, I'm going to resist. If you apply load, I'm going to resist. So between D and E, there is no resistance. It is just freely allowing us to stretch it. But after point D, it again starts resisting up to a point F. Okay. Now this zone is called as strain hardening zone. It is called as strain hardening zone. In this zone, with the increase in strain, there is an increase in stress. But there is an upper limit to it. It cannot go on resisting. So the maximum force that the material can take is called as the ultimate tensile force, and the corresponding stress is called as ultimate tensile strength, because it is the ultimate. There's nothing beyond that. Okay, so Fy is called as a yield stress, and Fu is called as the ultimate stress. Okay, and we see that after that it really cannot resist any more force, and the deformation goes increasing until it breaks. So this region is called as the post-ultimate stress region. Okay, perhaps these terms are new to you. You'll get used to it. Don't worry about it. So now let us look at these values here. So epsilon y. So Fy is called as yield stress. The corresponding strain is called as yield strain. So the difference between yield strain and the strain that we observe at point E is about 10 times. So if these are rough figures, okay, just to give a sense of understanding, and we look at the importance of this. But as of now, just stay with me, and just get the information in your system. So this is the yield strain. The strain corresponding to point E is about 10 times of epsilon y. Then the strain corresponding to point F is 100 times of epsilon y. Okay, so this is not to scale. Therefore, you might say, "Bhai, ये 10 है तो ये 100 कैसे हो गया?" It is not up to scale. If you want to look at a graph that is on scale, or close to what is on scale. It is this graph. So I've just drawn the other one for simplicity. So this is about 100 times of epsilon y. And finally, the breaking point is about 200 times of epsilon y. Now, what do these numbers mean? What do 10, 100, 200 mean? So, beyond Fy or beyond the yield point, there is not a lot of stress that the material can take, but there is a lot of strain that the material can take. Register this. Beyond yield point, there's not a lot of stress that the material can take, but there's a lot of strain that the material can take. Now, perhaps a little difficult question, but can someone answer me what does this mean or what is this property called? When a material can be elongated significantly before it actually fails. What is this property called? School mein sikha hai.
Elasticity.
Elasticity.
Specific. There's a specific term to that.
Malleability.
हमारी elasticity 0.8 की खत्म हो गई.
Ductility.
Malleability. Oh.
Ductility is the right term. So, ductility is a property of a material by the virtue of which it can be drawn into wires.
We can barely hear you.
Has it been all along or it's just now?
Just
Okay. I have some fluctuations in the network. Just let me know whenever that happens. I'll not try to repeat. So, the property by the virtue of which a material can be drawn into wires is called as ductility. Now, why are we talking about wires? Because wires are made by pulling a member, right? So, there's a lot of ductility in steel, meaning that it can undergo a lot of deformation before it actually ruptures. Now, okay, why are you talking about this? Why do we want our members to deform? Ideally, we would want our members to deform, right? We don't want, beams to sag and, columns to buckle. But why are we talking about deformation? Or, let me put it this way. Under what type of loading condition will you expect a lot of deformation in the members?
As a beam as opposed to a column.
Any member or the structure as a whole, in what type of loading condition will you expect the structure to deform a lot?
Eccentric load.
Centrally loading.
Sorry?
When it's loaded at the central point.
Any more inputs? It is a phenomenon. Okay, it is a disaster.
Eccentric loading. Earthquakes.
Earthquake, simple. By earthquake, when earthquake happens, the ground, there's going to be a significant amount of ground motion, depending on the magnitude of earthquake, of course. But for what we design for, we are expecting a lot of ground motion. Because of that ground motion and because of inertia of the structure, it is expected to undergo a lot of lateral deformation. So, if your member does not have capacity to absorb this energy and deform without failing, then your members are going to start collapsing and your structure is going to start collapsing. So, इसीलिए steel, has so much importance because it is very ductile. So, earthquake resistant, if you want to, build an earthquake resistant system, then steel is a go-to material. Of course, we do it in concrete also, but just look at the amount of ductility that it can take. So, it can deform 200 times more after it is yielded. In design, we say that yielding, the yield stress is the maximum stress. Uske aage we don't design it for that. So, after it has theoretically failed, it can deform about 200 times more. So, this is a very important property of steel, and that is particularly of importance in the design of structures for earthquake and wind loads or lateral loads. Okay, so that is why steel is so important. So we've looked at these points. I've mentioned what A, B, C, D, E, and F, G mean. Okay, just just look at this later on. So just to quickly revise, OA is the linear elastic zone, which follows Hooke's law. Hooke's law states that stress, which is denoted by small f, is proportional to strain, which is denoted by epsilon. So steel remains elastic and regains its original shape on unloading. That is called as elasticity. Okay, and it is a measure of axial stiffness. कि जितना उसका axial stiffness ज़्यादा है, the larger the amount of force you will have to apply to deform it. So it's a measure of stiffness. The slope of linear portion of the stress strain curve is known as Young's modulus of elasticity. okay, or modulus of elasticity. So E is basically stress upon strain. Now, this is a very, this is a very unique quality about steel, that irrespective of what is the grade of steel, so you use mild steel, high strength steel, super high strength steel, doesn't matter. The slope of this line always remains more or less same. Okay, we look at when you overlap graphs of different types of steel, we'll see this. But remember this as of now, that irrespective of the type of steel, the slope of this line, to you test any specimen, you test it anywhere around the globe, you test it using any universal testing machine, you are going to get a more or less the same slope. So steel has more or less the same modulus of elasticity, and the values are in the range of 2 into 10 to the power 5 to 2.1 into 10 to the power 5 MPa. What is approximately used is 200,000 megapascals, or 2 into 10 to the power 5 megapascals. So this is the value of E. Just register this. Remember this. We are going to be using this very commonly. So the average value of E, irrespective of the grade of steel, is 2 into 10 to the power 5 megapascals, or 200,000 megapascals. Then yes, AB is the nonlinear elastic zone. Hooke's law is not strictly valid, but the material is still elastic. DE is the plastic zone of the yield plateau. The material flows plastically without offering any resistance or without any increase in the stress. So this is a permanent deformation which occurs at a constant yield stress. This is also called as plastic zone, and this is a account for ductility of steel, a very important property. Now we're going to look at the formal definition of yield stress. You can just read along. So yield stress refers to the maximum stress that can be developed in the material without causing plastic deformation. In loose terms, what did we say? If you are within that straight line, you stretch it, remove it will go back to its original position. But there's an upper limit to that. That upper limit is called as yield stress. If you are stressing it beyond yield stress, there's going to be something called as plastic deformation. So the upper limit up to which the material is elastic is called as yield stress. Okay, and the corresponding strain is called as yield strain. Simple. You know what is E? E is equal to Fi upon E. Just flip the terms, you'll get the value of yield strain. Now yield strain is of the order of 0.00125 for mild steel, epsilon y. This is again a value you don't remember, but just to give you a feel of numbers. And the zone EF is called as a strain hardening zone. Okay. The strain corresponding to the strain hardening zone is about 10 types of epsilon y, and the upper limit, that is epsilon u, is about 100 times of epsilon y. So it can undergo a lot of deformation in the strain hardening zone. Now we talked about Fu, which is the ultimate tensile strength or the ultimate tensile stress. It is equal to the ultimate tensile load, whatever load that is you observe in the machine, 5,000, 6,000 kilonewton, whatever machine, and it is divided by the original area of cross section. Then you get what is called as Fu, or the ultimate tensile strength. Okay, and then Fg is the strain softening zone or the necking zone, wherein there's a large reduction in the cross section and ultimately there's a fracture, and it happens at an approximate strain value of 200 times epsilon y. So large deformation, large ductility. So these are the curves. Just to give you a sense of how high strength steel compares with mild steel, I've overlapped this. So the curve that you see below, so this one is the curve for mild steel. Okay, and then this is the curve for high strength steel. A little different. We are not going to get it into why it behaves differently, and how to look at that curve and so on. We're not going to get into details. This is just to give us a sense of how different grades of steel behave. What we observe is this line overlaps irrespective of the grade of steel, and hence the modulus of elasticity is same irrespective of the grade of steel. Okay, the difference between these two curves is obviously that it has a high yield point and it has a high yield stress and it has a high ultimate stress, but everything comes at a cost. Now, though it's perhaps not very important, but just to mention this, when you increase the strength of steel, you compromise with its ductility. Okay, so higher your x value, higher your y value, lower is going to be your x value. Okay, so just to quickly demonstrate what I mean. So if this is your curve, if this is mild steel, so this is your yield stress, this is your ultimate stress. Your high strength steel is going to have a curve that is something like this. Okay, so what we have done is we have been able to accomplish a higher value of FU, but what happens is we have compromised on the ductility. So everything comes at a cost. And how do we move from mild steel to high strength steel? We play with its chemical composition. Perhaps we use a large amount of carbon in that. And carbon is brittle. And therefore, it is strong but is brittle. Just like concrete. Concrete is strong but it is brittle. So when you increase the strength of steel, you achieve a higher value of FU, but you compromise on ductility. So opting for very high strength steel is not always a good option. You know, there's always a calculation that you have to make at the back of the mind as to what is important to you. You know, if strength is not that important, if ductility is important, if you're building some steel project in Uttarakhand, where earthquake ka bhai bahut tension hai. So at that time, in such locations, in places like Nepal, where highly seismic zones, perhaps go for a lower grade of steel that will help you achieve ductility. So this is extra ka gyan. It's up to you how much to to register it, remember it. No problem. So I think we've already 12:20. Yes, our 100 minutes of over. So we'll stop here. There is a lot of information that is passed on in the last half an hour. I want you to just try to read it again after the lecture, not on next Friday, but in this couple of days, and just try to understand if you are okay with whatever has been taught. If you understand it well, if there's any problem, if you think that perhaps this is going too fast, I can always take feedback in the next lecture and work on it again if you think you do not understand it. As of now, do you have any questions?
I don't have a question, but is it possible for you to share this presentation with us so that we can go back to it whenever we want to revise or anything?
Yes, normally I share the presentation in a couple of days. That
Okay.
gives you enough time, for prepare for the next lecture. So,
Yeah, no problem. Thank you.
yeah.